Now, when one designs in China, how does one design a super tall building? And of course, one possibility was to think of it in traditional terms. Another possibility is to think of it as something quite different from that. What we in fact did was to try to find a way of dealing with the basic dynamic of a tall building as that which was anchored into the earth and created a relationship between the earth and the sky. I mean, that's sort of the essence of the tall building. The dramatization of that particular fundamental issue of the relationship between earth and sky became somewhat of the genesis for the building. Ancient Chinese represented, in their burial tombs, they represented the earth with a square prism, and as you can see, the horizontal striations of dark stone, and the heavens they represented as a circular disk of light stone. And so it occurred to us that the possibility of creating an extremely simple building, because within this cacophony of 80 tall buildings, each of which had an entirely different architectural style with no regulation whatsoever, the intention at this time was to be able to create the simplest possible building that created an abstract, a powerfully abstract relationship that hopefully was based on something that had a strong connection to Chinese history, without resorting to any sort of pagoda designs. So that brought about then the transformation of as at the top you can see the, up on top here you can see the square prism, and that's, I did it again. That square prism was interacted by a series of sort of cosmic arcs. And the carving of that prism into the form you see at the bottom was the basic idea behind the building itself. So when we talk about the building being a relationship between the circle and the square, it is really the diagram on the right-hand side. Those are the circles. That is the circle, this cosmic arc cutting through the building that would form the genesis of the building. You'll see why there's a confusion as to what the issue of the circle really is after I show you a couple more slides. But what this shape does is generate fundamentally two different types of floor plates. One is basically a square, which is ideal for office space, and the other is basically sort of a lozenge shape, which is ideal for hotel space. And we have two fundamental programmatic components. We have a hotel at the top, we have at the base of it office structure. There are many other components as well, but those are the two fundamental driving geometries. This building was presented to the Chinese authorities in 1993, I believe, Josh, if I'm not mistaken. And at that particular presentation, there were 14 professors of architecture, each of whom had 1/2 hour to respond to my 10-minute presentation. It went from Chinese to Japanese to English, so my ability to really get the essence of the criticism was somewhat diminished, but nevertheless, the first presentation, I thought it was going to get this all off to a great start. There was a wonderful elderly woman that had a beautiful smile on her face, and she got up and she looked out at me and she said in English, and these were the only words that were spoken in English that day, she said, well, perhaps this building is acceptable, but it certainly isn't desirable. And then it sort of went from bad to worse. But we never really got a synopsis of the criticism that day, but it arrived via the Hong Kong newspapers a while later. The translation of the building from square to line on the top, from the heaviness of the earth to the lightness in the sky, is best illustrated by this diagram, which shows all of the transformations of the floor plates. There was a need for an aperture on the top of the building, and the aperture that seemed to be most successful was a circular aperture. All of that linked very nicely, I believed, into the moon gates that are regularly present in Chinese gardens, and all of the critics of the building saw this. They saw the Japanese flag, which for a building that is to be the tallest building in China didn't get things off to a good start. So I understood after all of that what the criticism was about. I went for an emergency meeting with Mr. Mori and the mayor of Shanghai in Tokyo for a 1-hour meeting, and I suggested placing a bridge across the circle, sort of the symbolizing the joining together of two sides. And I would receive this wonderful letter. There's actually a gold seal on the bottom, which we should have emphasized here, but nevertheless, in great appreciation for having sort of dealt this Henry Kissinger-like contribution to the dialogue between two countries. But that didn't necessarily last that long. The idea behind the circle was to try to create a solid void relationship between the Oriental Pearl TB Tower and our tower, which we turned in direct axial relationship with the Oriental Pearl TB Tower. And at the top, referring back to Mr. Mori's P.T. Barnum days, placing a gondola ride that went around that circle itself, and that whole inverted cone down at the base there is a queuing device, much like the Guggenheim Museum, but everybody waiting to get onto the gondola. That probably would have been a dramatic entity, and we went a long way with the structural design of this. Les Robertson did, and we did complete designs for it, but it was ill-fated, as I'll show you later. One of Mr. Mori's fundamental intentions with the tall building is to make it a civic entity. He did it in Tokyo, he did it in Shanghai. In other words, if the top of the building can be something that is for everybody, for him then the building becomes not just a representation of the private enterprise, but it becomes something that is a civic symbol. And we couldn't agree more. The building with the circular form ultimately met with great resistance, particularly after the internet started to become a means of expressing one's opinion, and the relationship of the circle to the place was really perceived as unacceptable. And so what we ultimately did is translated it into a form probably more natural to the geometry of the building. All of this up above here is space where observation space, one can come up and take a bridge across the top, which I'll show you a photograph of. On the top of the hotel, which is down in here, there's a 3-story stack of dining facilities that's called Club 100, or Century 100, excuse me, and it is a incredible series of rooms. And I can say that because the entire Park Hyatt Hotel, which is in the blue, was designed by Tony Chi, who is an architect here in New York, and is perhaps one of the most beautiful hotels that I've certainly encountered any place in the world. And it is a place of tremendous energy. And then at the top, this is that 3-story stack of restaurants that I told you about, which is constantly filled and impossible to get a table at. This is the entrance then to the observation, and that is, all of this is queuing for tour buses and all of that. One goes in and experiences this type of world, and the very top has a bridge with a glass floor which looks down to the city below.
Hi, my name is Bill Baker. I'm the partner in charge of structural engineering for the Skidmore, Owings & Merrill office here in Chicago. I had the pleasure of leading the team of structural engineers who designed the Burj Dubai. My engineers and I work very closely with the architects, the electrical engineers, mechanical engineers, and plumbing engineers, as well as some very important outside consultants such as the elevator consultants, the wind tunnel consultants, and others to develop this design. Now, this design really is a Swiss watch. We need to work very closely with all these other professionals to come up with this building that's quite integrated. Now, the structure itself is the part of the building that resists the natural forces of nature, such as wind, seismic, and gravity. But by doing this in a smart way that works with all the other systems of the buildings, you get an economical building which you could actually afford to build, which is very important when you're trying to achieve something of this monumental height. Now, one of the other very important things about a tall building is the way it behaves with the wind. Now, if you have any object in the wind, as the wind flows past the object, it'll peel off and create vortices. And each time one of these occur, they put a little pulse perpendicular to the direction of the wind. And if these pulses occur at the natural frequency of the tower, you can get very large forces. This is very much like a child on a swing set. When you have a child on a swing set, the child will sit on the swing, and by kicking their feet at the natural frequency of the swing, they'll get going higher and higher and higher and higher. Now, in a tall building, what we try to do, we try to confuse the wind. Because a building will also be an oscillator, like a swing is an oscillator, it'll have a natural frequency where it tends to want to vibrate. And if the rate at which these vortices occur matches the natural frequency of the building, you can get quite large forces. So the rate at which these occur are related to the width of the object and the shape of the floor plate. And if you vary those two parameters, you can essentially confuse the wind. It's like having a child on a swing where one foot is going up and the other foot's going down. The child wouldn't go very far at all. Every segment of the building behaves differently than the segment above it or below it. Say the wind is coming from this direction. Here you see it's hitting a broad face, and the vortices would peel off. But if the wind was coming at this direction, it hits essentially what we call a cutwater, and it's fairly benign. So what we want to do is we want to control the behavior of the building, or control the forces that are on the building when the wind is hitting the broad face. And we do that by changing the shape of the floor plate. We found that there was one particular direction that was more active than others. So we actually rotated the building 120 degrees to put that more active direction in a direction where the wind is less likely to come from. Initially, the setbacks occurred in a counterclockwise manner, but based on the wind tunnel studies, we concluded it was beneficial to have the steps occur in a clockwise manner. So through this process of changing the shape of the building, we were able to greatly reduce the forces on the building. And without that process, and without working with the wind tunnel consultants, doing many, many tests in the wind tunnel with RWDI, we would not have been able to achieve a building that is as tall as this building.
My name is Lawrence Novak, a structural engineer working on the Burj Dubai Tower. In this student demonstration wind tunnel, you can see that as the wind blows at a rectangular building, the vortices become organized and cause motions perpendicular to the wind direction. A vortex is a swirl of air similar to a mini tornado that rolls past the building. When we replace the rectangular building with a tapered triangular building similar to the Burj Dubai Tower, the vortices cannot become organized, and this greatly reduces the forces and motions. In a commercial wind tunnel used in the design of the Burj Dubai Tower is based on the same principles as this simple demonstration, but with very precise geometry and sophisticated instrumentation.